In class, we've been talking about building variable input length PRFs because these are extremely useful objects. And we realized that we don't actually have any way to do this yet. We have fixed input length PRFs like block ciphers, but we don't have ones that have big domains, the domains in particular that will allow us to take variable input length strings. So one of the constructions that we proposed and that we've seen now appear a couple of times is this one. You start with a function family E, which takes a key from some set K1. It takes an n-bit strings as input and outputs n-bit strings. And we think of this as being the fixed input length PRF in the construction. We also have this function family H, which takes in keys from some set K2, strings from some domain D, which we think of as being lots of strings of all kinds of lengths, outputting strings of length n, and this is going to be the hash. And we define this function family F, which takes in keys from each of the two key sets. It takes in strings from the domain of H and outputs an n-bit string in the following way. When called on a string X, one first hashes X and then takes the output of the hash, which is n bits long, and runs it through this function E under key K1. That's our construction. And the claim is that if this thing is a good PRF over fixed input lengths, in particular n-bit strings, and this is a collision-resistant hash, then this is a good PRF, but now with a variable input length domain. And the intuition for why this is true is pretty strong, right? The idea is, look, if this thing here is truly a good PRF, then we can think of replacing this by a random function rho. Now, until you find a collision in this thing, then all of the inputs to that rho are distinct, which means that you're getting now outputs of this information theoretic construction rho running on the outputs of the hash function. As long as these things are distinct, then the outputs of rho are all independent uniform random strings, and that is the exactly distribution that you would get if you had instead a big random function R, where this is uniformly from all functions that map from D to N, which is, after all, the mapping that F provides, right? So remember, we're trying to argue that F under secret random keys K1, K2 is computationally indistinguishable from a random function with the same domain and range. So again, the intuition is until you find a collision in H, all of the outputs of this thing are identically distributed to the outputs of this thing. And so up to finding a collision, there is no test that can distinguish this from this because their outputs are identically distributed. And that's why you need H to be collision resistant. So that was the intuition. It turns out we don't, in fact, need full collision resistance. We can get away with a weaker property. In particular, computationally, AU will suffice for this proof, and we'll see that in a bit. Okay, so how are we going to do this proof? Whenever we have one of these claims, the way we approach it is to assume that you have an efficient adversary A that breaks the property sort of on the right-hand side of the implication. So in this case, assume we have an adversary A that breaks the PRF property of F. We're going to show that means there either exists an adversary B efficient in its execution that breaks the PRF property of E, or we have an efficient collision finder C for H. Right? Recall that if you have a if and something, then when you turn it on its head and say, well, if not this, that means you have either not this or not this. So we're going to start. You can approach this proof either way. You can either start by trying to show how you would build the collision finder out of this PRF adversary A, or you can start by trying to build a PRF adversary B out of A. For me, it's easier to start with this piece first, so let's do that. So here's my adversary B. Recall that it is going to be playing the PRF game attacking E. So its oracle is either E sub K1 for some random key K1, or it's a random function rho. And both of these things take in n-bit strings and output n-bit strings. Right? So B is attacking the PRF property of E. We're going to start by having B initialize this table for reasons that will become clear in a moment, but I say here it's to prevent against having B asking repeat queries up here, and we'll see when that happens. But anyway, initialize this table to T. When we have a table, we always assume that it's initialized everywhere to undefined, meaning that for every value, every position in this table, there's some marker there that says this position is yet undefined. This will become clear in a second. Then we pick a key K2 for the hash, and we run A. And when A asks a query X, we just do what we're supposed to do, right? B is supposed to be trying to simulate for A this construction F. So what does it do? Well, what does F do? When on input in X, it hashes X. So that's what B does. It hashes X using this key K2 that it picked to get a value Y. And now here's where the table comes in handy. If the table at position Y is undefined, then we actually send Y up to the oracle to get a value, and we assign to the table at position Y that value. So really, what is this table T tracking? It's tracking what are the inputs and outputs of oracle queries that B makes to its oracle. Recall that this oracle is either going to be so Z is effectively going to be E sub K1 of the hash of X, because it's E sub K1 of Y, where Y is the hash of X. We'll be simulating this when B's challenge bit is 1, or we'll be simulating this when B's challenge bit is 0, because in this case, B's oracle is row. In any case, we take this value Z and we return it back to A. Now, why do we have this check? Why not just send Y directly up to the oracle? Well, the reason is if there's an X that's asked sometime that defines value Y, then the first time we go into the table position Y, it'll be marked as undefined. We'll call the oracle, and we'll actually define a value at that position to clear the value Z. If later on there's some X prime that's asked that produces the same value Y, in particular a collision, then this table position will be defined, and we'll just go ahead and skip these things and return whatever we returned before. And that's what we're supposed to do, right? If you get a collision in the hash, then the construction will return the same value twice, no matter whether the actual sort of outer piece is E sub K1 or row. We do this to protect ourselves, because if we had an X and an X prime that gave us the same Y, we can't ask the same Y twice to this oracle. Recall, that's part of the PRF game. You can't repeat queries. And so we just store input-output values in this table, and if we ever detect a collision, then we just use the table to return the appropriate value. Okay, so here we're simulating either the construction F, right? This perfectly simulates the construction F, or we simulate some related construction, except now where F would have called E sub K1, this related construction calls a random function row. So when our bit is 1, we perfectly simulate, and when our bit is 0, we don't, but we'll see that that's kind of okay. In any case, at some point, A is going to halt with some output bit D prime, and I'm calling this D prime to distinguish the fact that in A's game, there's some challenge bit, because A's game is a PRF game. Remember, A is attacking the PRF property of F. So there's some challenge bit D in A's PRF game. And so I call A's output D prime to distinguish that from the challenge bit B that's in this PRF game that's determining whether or not the oracle is E sub K1 or row. So when A halts with its guess at its bit, D prime, then we're just going to go ahead and output D prime and halt. And we'll see that this makes sense, in particular because when our bit is 1, we simulate this, which is exactly what A would get if its bit D was equal to 1. And when our bit is equal to 0, well, we don't necessarily simulate what A would get in its experiment if D was equal to 0, because that would be, in particular, this thing, the big random function. But what we're going to argue is that, in fact, this thing is just the same as this, so long as there's no collision here. And so by returning whatever A's output bit is, we won't hurt ourselves. We'll always be doing the right thing in this case, and we won't hurt ourselves too often in this case. In particular, anytime we would hurt ourselves by returning A's bit when our bit is 0, in that case, we'll win the collision game. Okay, so hopefully that's all clear. And also, I don't know if you just heard in the background, they're doing construction in the building, and they're drilling both in the floor under me and the ceiling above me. There it is. It sounds like a doctor's office, like a dentist's drill. I apologize if you can hear that. Okay, so let's go on with the analysis then. Let's proceed with the analysis of our constructed B and see how good a job it does. So keep in mind, what we want to show is that B is actually good at breaking the PRF security of E, and we want to show this in particular as a function of how good A is at breaking F. So as usual, we're trying to measure the PRF advantage of B, and we always take this first step of conditioning the probability that's within that advantage statement based on whether or not the challenge bit in that PRF experiment is 1 or 0. Man, that is super annoying. Okay, so when the bit in this PRF experiment is 1, that means that B's oracle is E sub k1. And we've already argued that in that case, B perfectly simulates the construction F. This event here, that the experiment outputs 1, happens by construction of B if and only if B outputs 1, right? The experiment outputs 1 when B guesses the bit, which means B outputs 1, because that's the bit. B outputs 1 by our construction if and only if A outputs 1. So whatever this probability is, it's the probability that A outputs 1 when its oracle is the construction, right? Because that's what we get when our oracle is this. Well, that's nothing more than the probability that A wins the PRF experiment against F when its challenge bit D is 1. Because when its bit D is 1, its oracle is this. So these two probabilities are the same. That's the easy part. Let's look at the other piece now. When the challenge bit in B's PRF experiment is 0, then we know that the oracle here is a random function, right? And we usually play this trick of saying, well, the experiment outputs 1 when B guesses the bit, and B guessing the bit here would mean outputting 0. It's easier for us to think about B outputting 1 because we've already sort of thought about that. So we just switch this to be 1 minus the probability that the experiment outputs 0 when the bit is 0. The experiment outputs 0 exactly when B outputs 1. So this thing outputs 0 when B outputs 1, which by construction again is if and only if A outputs 1. So this probability here is exactly the probability that A outputs 1 when its oracle is this thing. And that's what we're going to need to analyze to finish out this thing. This piece is done. We just need to get a nice bound on this piece. So recall the intuition is that this construction, this oracle, if we provided it to A, this thing is indistinguishable from this big variable input length random function R until A asks some x and x prime that are different and they give the same hash. Right? That was our intuition from earlier. So we're going to do actually do the analysis of this probability. We're going to just do a simple game playing argument. In particular, we're going to start by, let me scoot this down a bit. So we're trying to analyze this, the probability that A outputs 1 when its oracle is this row of HK. And the first game we're going to set up is this G0. And it's going to look a little funny because it's got some notation you haven't seen before, but let's just work through it. So G0, it's essentially going to be just like the PRF experiment when A is provided this thing as an oracle. So G0 picks the key for the hash, which will allow us to implement this. And then it runs A with this oracle. I'm now calling script F as opposed to script O because script O was the oracle in B's PRF construction. What does oracle script F do? Well, let's look over here. This thing's actually going to implement this oracle row of HK2, which is exactly the thing we're trying to measure here. So here's how it's going to work. When X is queried, we just pick a random Z from among the n-bit strings. Then we hash X, the thing that was passed in, and that gives us some value Y. And then we're going to do this funny check here, which I'll explain in a minute. And then we're going to return a value z. And what we're hoping, let me just go ahead and put this up here. Let's look at each of these pieces. I'm claiming that this oracle implements this in this game. Okay, so let's look at the pieces. Z is first sampled from strings of length n. This is the value that we're going to want to return. Because if we can return this all the time, then that means that this oracle is behaving like a random function with a big domain. And in that case, this thing will actually be acting like a capital R. And that's, sort of where we're going. We'd like to be able to argue we can get there. However, we're not going to be able to return this uniform random value. And in particular, we're not going to be able to return it when there's a collision in this thing. That's what we've talked through already. So we pick this value and we say, okay, let's hang on to this. Then we hash the input x. That gives us a y. And now we check a table. This is a table T. It's a different table T than the one that was in our adversary B. Sorry for the collision, but this is a table T. It's been initialized everywhere to undefined. This table is going to be used to associate hash outputs with oracle outputs, just as it did before. In particular, if when we hash x, we get a value y, we look at that position in this table. If that's undefined, then that means that, if that's not undefined, okay, if it's not undefined at position y, then that means that some previous call produced a value y that caused this position to be defined. And what does that mean? It means that there were two calls to f, some x, and now an x prime, that produced the same value y. Because the first one would have, the first x of the colliding pair would have produced a y. It would have looked at this and said, oh, it's undefined, so I can skip this. And what happens? If I skip this, then we just assign at position y in this table this value z, which, because we skipped all this, is just this random value. And then we return z. So on that first value, what we do is what we're supposed to do. It would be a distinct value coming out of this. This thing would then give you a uniform random output, and that's indeed what we do. We pick a uniform random output, we hash. It's a value y that's not been previously seen in this table, so we skip all this. We assign to the table at that position the value z, and then we return z, a uniform random value. If later there's an x prime that's asked, we'll pick a new value z that we'd like to return. We hash x prime to get a y prime, and we realize, oh, in fact, y is the same as it was, y prime is the same as some previous y, which means that position in the table is no longer undefined. Well, so if we're going to implement this thing, what do we have to do? If we have a collision in this, we have to return the same value from this that we returned before, because that's what this thing would do. So that's what the table allows us to take care of. When we find that we've got a y for which the table was previously defined, then we jump in here to this thing. We're going to keep a Boolean flag called bad, and we're going to set it to true, and we'll see why in a bit. This flag bad was initialized to false implicitly. So if we jump in here, we set this flag bad to true, and then we actually do what we're supposed to, which is we take the previous value that was assigned here, we write that into z. We overwrite the random value that we chose. We overwrite it with the value that was returned before, and then we come out of this if. We just write that same value back again, so we haven't done anything. We read the value out and then read it back in, and then we return it. So in the case that we have an x and an x prime that give us the same value y, we do what we're supposed to, which is return the same value out of this that we did before. Okay, so these are all some notes here on the side to help you sort of track what's going on. And I'm going to turn those off now to make some room, but you can always pause the video to stare at them. Okay, so I'm going to now define here a second game, G1, and I'm going to do it just because so little changes between G0 and G1, I'm going to do it sort of on top of it. So I've put a green box around this statement, and I want you to interpret this in the following way. Game G0 includes the boxed instruction, which is this one. Game G1 does not include this statement. So in particular, in game G1, when we hit this if and it evaluates to true, then we drop in here, we're going to set the bad flag and then do nothing else. And so the claim is that in G0, we still do what we did before. We claimed is that we implement this oracle, right? We hash and then we run it through this small random function. And in game G1, I claimed that in G1, the oracle f actually implements a big random function r, and let's see why. In G1, so in G1, this instruction is not here, right? So in G1, it's the same up here. This is all as before. The oracle f now, when called upon x, it picks the random value z. It hashes x to get a y. It checks to see, has this y ever been seen before? Is this a collision? If it is, it drops into this as before. It sets bad to true, just like before, but it does not do this, which means that the value assigned to, there was a value here before, and now that's overwritten by this random value, and we just return that random value. And so now, no matter what happens, no matter what x is asked, if there's a collision here or not, we always return a uniform random value here. And that is exactly the behavior of this big capital R. Yeah, so that's what I just said. To notice that in G1, in game G1, the oracle f always returns a uniform random n-bit string, and that's what supports this claim. And so we can conclude is the following. So right, this note's on here again just to remind you later. So G0 simulates an oracle for this thing. G1 simulates a random function that maps from D to N, which is exactly this thing R up here. And here's the new piece. G0 and G1 are what are called identical until bad. What does that mean? It means that their behavior, the behavior of these games, in particular the behavior of the oracle, notice nothing changes between the games here. A runs with some oracle, outputs a bit D prime, and the game returns it. What's different is the behavior of this oracle, and this oracle behaves equivalently, identically in both of these games until bad is set to true. Why? Because when bad is set to true in game G0, this happens. And when bad is set to true in game G1, this does not happen. It's only at that point that the executions diverge. And there is a very nice result called the fundamental lemma of game playing, which says the following. The first thing is the probability that in G0, when A runs inside of G0, the probability of the event bad being equal to true is the same as the probability that when A runs inside game G1, bad gets set to true. Why is this the case? Well, there's some mathematical, some technical stuff you have to work out, but the intuition is this. This probability is over what? It's over the coins of G0 and A. This probability is over the coins of G1 and A, right? The coins, the random choices. We call them the coins. So fix any set of coins for both the game and A. If you fix any set of coins, that means that this random sampling is fixed. Some particular key is fixed. Any coins that A would have flipped, those are fixed. Likewise, anything here is fixed. So it's as soon as you fix the random coins that underlie game G0 and A, or game G1 and A, as soon as those coins are fixed, then you have a deterministic execution path when you run A inside of G0 or A inside of G1. Well, what does that mean? Any coin string, any deterministic execution that when G0 runs with A would lead us to set bad being equal to true. Prior to bad being equal to true, the executions of G0 with A and G1 with A are the same for any fixed coin strings, right? Because they're identical until this point. So that means that the only place at which they diverge is when bad is set to true. But the probability of bad being set to true is identical in both of these games because for any particular coin flip string, they're going to all lead to they're going to lead to bad being equal to true in G0 if and only if it happens in G1, right? Because prior to that, they're identical. So that's this hand-wavy proof of this statement, which is in fact true. And the second part of this fundamental lemma of game playing is the following. If I think about the probability that A causes G0 to output 1, right, which means that A outputs a 1 itself. If I condition this probability on whether or not bad is set to true, so if I condition this on bad being equal to true, then I'll have this thing, condition on bad not being equal to true, and there would be here the probability of bad not being equal to true. But I'm just going to go ahead and upper bound that by 1, because I can always do that with a probability. So this is going to become an upper bound now. The second term in that conditioning would be this thing conditioned upon bad being equal to true. So that would appear like here, multiplied by the probability that bad in fact is equal to true in this game G0. But this conditional term here, I'll likewise upper bound that by 1, which then gives me this statement. So this is just by straight doing conditional probabilities. There's nothing fancy here. There's nothing about the fact that it's a game playing. It's just conditional probabilities. I can always do this. And then by the first thing, I can say, well, this probability here is the same as this probability here. So I can replace that with this. Moreover, if I think about the probability that A causes G0 to output 1 when bad is not equal to true, the probability of that when bad is not equal to true, because G0 and G1 are identical until they are true, then the chance that A outputs 1 in G0, given that this never happens, right? Bad never set to true means this never happens. Well, if this never happens, then what do we have? We have exactly game G1, because you only ever execute these statements and these statements. And so the probability that G0 outputs a bit 1 from A, given that these statements never happen, is exactly the probability that G1 running with A outputs a 1. So this conditional piece can be replaced by this. Great. So we're going to use this. I'd suggest you maybe stop and pause and stare at that too. So how are we going to use this? All right. So we'd argued a moment ago that in G1 in particular, this oracle F is always implementing this big random function R. So the probability that G1 outputs a 1 is exactly, because G1 outputs 1 if and only if A outputs 1. This is the probability that A outputs 1 when its oracle is this big random function R. But what is that? That's exactly the PRF game that A would be playing. Yeah, there in that game, it either has F or it has a big random function R. It has a big random function R when the challenge bit in this game is 0. So this probability is exactly the probability of A in this PRF game against F, causing the experiment to output 0, meaning that A doesn't guess the bit 0 and guesses 1 instead. That causes this thing to return 0. So this is exactly this. The probability that A outputs 1 when its oracle is this, but we just argued that this is exactly this. Thus, the probability that in game G1 A outputs 1, that's exactly this probability. And that's awesome, because we're going to start being able to now work this into our derivation. So let's see where this is going. Oops. There we go. Okay, so let's take this that we just established and scoot up a bit here. So recall, this is the piece that we were trying to bound the probability, what happens, the probability that B outputs 1, which happens if and only if A outputs 1, when B's oracle is this little random function rho. We argued that when B's oracle is this little random function rho, then that means we simulate for A this thing. And recall, that's exactly what game G0 does for A, right? So this probability here is this probability here in words, the probability that A outputs 1 when its oracle is this thing. But by construction, that's exactly this probability, right? G0 outputs 1 when A outputs 1, and G0 implements this oracle. So we get this equality here. 1 minus this is 1 minus this. But then we just argued, using this fundamental lemma of game playing down here, that we can upper bound this thing by what's in the parentheses over here. And if I upper bound this and I subtract it, that means I get a lower bound, right? You know, if you like upper bound and you subtract, and if you have to flip it around. So this thing here is at least 1 minus the thing that we replaced this by, which is all that. And we just said a moment ago down here that the probability that G1 outputs 1 when running with A, that's exactly this. So we got that from down here. This we just get by distributing this minus sign through here. And notice that 1 minus this thing is exactly the probability that the PRF experiment outputs 1 when d is equal to 0, right? It's just playing our trick in reverse. So once we've done that, okay, sorry, I had to pause there because I had a knock at the door. Anyway, let's pick up where we were. So, right, we got to this point, and notice we're looking pretty good now, because what do we want to do? We wanted to capture B's ability to win its PRF game against E in terms of A's ability to win its PRF game. And we're looking pretty good in that respect, because when we analyze the chance that B wins when its challenge bit is 1, we got that directly to be in terms of A's ability to win its game against F. And for the other piece, B's ability to win when its bit was 0, well, we went through some moves, but in the end, we did in fact arrive at an expression that's in terms of A's ability to win. So we're looking pretty good. We've got both pieces, A winning when its bit is 0, and A winning when its bit is 1. So we're pretty close to being done, because we know in the end we're going to combine these two pieces together, and that's going to result in combining this with this. And we know we have this piece and this together. That's going to end up giving us A's advantage. So really all that remains is to bound this piece at the end, the probability that A causes bad to be equal to true in game G1. So let's return to thinking about game G1, in particular the chance that it causes bad to be set to true. When is bad set to true? Well, we've already established that that happens exactly when, so we're in game G1, A is making calls to this oracle F, and recall in G1 we've established, because this boxed instruction is not there, that this oracle F actually just implements a random function R with the variable input domain. And in particular, the only time that bad would be set to true is when F is asked an X and an X prime that give us the same value of Y, because that causes this to be true, right? In particular, when there's a collision here. So what we're hoping to argue is that in game G1, the probability that A causes bad to be set to true is very closely related to the ability to make collisions here, collisions in the hash. And we'll see that in fact it's not just collisions, well, I mean it is collisions, but it's not collision resistance that'll end up popping out as the needed security property. So what we're going to do to make this all super clear is we're going to go from game G1 to a new game, G2, which is here. Okay, so let's look at what we've done. So recall, in G1, this oracle is always returning a random value. And notice that since this instruction is not here in game G1, then it doesn't actually matter what we assign to this table, because what always is returned is this random value, right? What we assign to the table is irrelevant. All we need is some way to know that the table has been defined at that point. Well, so we can capture that functionality by basically just saying, okay, let's keep track of what's been asked. So here's what we're going to do. In G2, we're going to have this, this set X. And these are going to be the set of values that are asked to F, and we're going to start it with the empty set. And then the rest of it is as before. The key for the hash is picked. A is given the oracle for F. Now let's go looking for the oracle for F, and then we'll come back. The oracle for F now does the following. When asked X, it adds X to this set, calligraphic X. It picks a random value Z and returns it. Let's make sure that's correct. When this oracle is asked X, the value returned is uniformly random. When this oracle in game G1 is asked X, we do a bunch of stuff. We pick this random value, we compute the hash, we check the table, and then what do? We return the random value. So indeed, for every X, we return a random value, and that's exactly what happens over here. When A asks X, we return this random value. What's different is we're no longer keeping track of this table, because in G1, whether or not this statement is true, it doesn't change anything about the way the oracle behaves. In fact, every return value from this oracle is uniformly random. So what we're going to do is just keep track of what's been asked. And rather than looking for bad being set inside this oracle, because every value from this thing returned, every returned string from the oracle is just a uniform random string, in particular, it's independent of whether or not bad is true, right? This doesn't change the behavior of this oracle. So, A could just as well have picked all these random values itself. We can check for whether or not bad is true, in other words, whether or not there's a collision, after A finishes running. Because from A's perspective, whether or not bad is true changes nothing about the behavior of this oracle. So that's what we're going to do. A runs with this oracle. It asks X's, and we're just going to keep track of what those X's are and then look for a collision among them later. Return this random value. A outputs its bit D prime. And now, whereas here we would have returned D prime, we're just going to ignore D prime and what follows here. And that's fine, because if you think about the probability that we're trying to measure, we're trying to measure the probability that bad gets set to true. What A's output is irrelevant for the probability of this event. So A outputs its guess D prime, who cares, we ignore it, and now we check. If among the values that were asked to this oracle, there's an X and an X prime, such that they're different, and they hash to the same value, then we set bad to be equal to true. And by the argument we just made, the probability that this happens is exactly the probability that this happens over here. Because again, the oracle's responses are always uniformly random no matter what this is. So we could check for this after A runs, and it wouldn't change the behavior of the oracle. So that's what we do. We just check to see, we're basically now keeping track. What's been asked, return the random value. After A finishes, let's look for a colliding pair. If we find a colliding pair, bad's equal to true. That same colliding pair would have caused bad to be equal to true over here. And you can't argue that, well, maybe A would have asked different queries over here than it would in this game because, this oracle somehow, is checking bad true. You can't make that argument precisely because, as I said, the responses from this oracle are always uniformly random and independent of the value of bad. And so there's no way to adapt. There's no way for A to adapt its queries here versus here because these oracles are identical. So the probability of bad being set in G2 is the same as it is in G1, and now we're pretty much home free because, as we've done before where we play this dirty trick of moving bits around until after the adversary's done running. How do I get rid of that? Go away. Go away. Seriously? Okay. So now we're in G2, and we've argued that the probability of bad being set to true in G1 is the same as it is here. And so we can conclude by adding the next layer that this is just equal to the probability that in G2, bad gets set to true. And now check this out. We can, since this is never used until after A runs, because it's only used here, we can just move it till after A runs. And now, what do you notice? The adversary A, bad gets set to true if A actually asks an X and an X prime that collide, but where everything that A does is independent of the key. So we can move the key to afterwards. But what does that mean? In the collision kind of game that we think about, in the normal collision resistance experiment, a collision finder would have to have the key, right? It gets the key and then has to find a collision. Here, we're basically saying bad is being set to true. In other words, we find a collision, even if this key is picked only at the very end, right before we have to check this thing. So what we're going to do is argue that, in fact, there is an adversary C. I want to bound this thing now by a probability of winning a collision finding game, and in particular, winning the computational AU collision finding game. Here's the adversary C that's going to do this. Basically, C is just going to use A to ask these queries, and then when it's done, it's going to guess a pair and output it. So C runs A. When A queries X, it just does what's here, right? It adds X to the set, picks a random value, returns a random value to A. It simulates this perfectly. At some point, A halts. When A halts with this bit D prime, C is going to ignore D prime. It's going to look at these set of things, and it's going to pick two of them without replacement, meaning it's going to be sure that this and this are different from this set, and it's going to output that pair. That's it. So now what do we notice? Look, if bad is equal to true in this game, that means there does exist at least one pair for which this is true. And so if we're picking a random pair out of this set, then the chance that this C, who notice doesn't have the key, but still maybe manages to find a collision, that's C playing the computational AU game. C doesn't get the key, it outputs a pair, and it wins if it finds a collision. But that's exactly what happens when bad gets set to true over here. So what we can conclude is the chance that C wins the computational AU game against H is at least, well, it's at least this. The probability that bad gets set to true over here. But bad being set to true over here happens if there exists a pair. But C actually has to find a pair. So by having C sample a pair at random, how many pairs are there? Well, if there are Q queries that A makes to this oracle, that means then there are Q values that are in this set X, likewise Q values in this set. How many pairs are there? That's Q choose 2. So if we're picking one of those pairs at random, then the chance that we pick a pair that would cause bad to be set to true over here is at least 1 over Q choose 2, right? Because we're picking one of the pairs uniformly. So we can conclude this. If that's not clear, go back and listen to it again. In any case, now we can move on because, what can we say? So, let's put all this stuff together now. In the first part, maybe I'll scoot over a little bit. So in the first piece, the probability that B wins the PRF game is, we know, a half times the conditional probability. Well, what do we argue? It's a little bit fast. This we would condition on B being equal to 1 or B being equal to 0. We argue when B is equal to 1, that's the same as this, so I'm going to substitute that in here. And in the conditional probability here, there'd be a half sitting in front of each of these terms. So we substitute that in. And by the argument we just gave, the second piece of this conditional probability is upper bounded by, well, it was upper bounded by this minus this. But then we just said that this is actually upper bounded. Yeah, this is upper bounded by, take this and put it on that side over here, by that term. So we substitute that piece in here. Yeah, that's what we just argued. And the definition of the CAU advantage is just this probability. There's no scaling. So by substitution, we end up at this step. But look, half times this plus half times this, that's just the probability that A wins its game. So we can replace all of that with this, and we pull this down here. And so if we rearrange, what do we get? You move this to that side. This is an upper bound because we had this upper bound here. So we get that when we pull this to that side, we multiply through by 2 and subtract 1, we'll get the following, that B's PRF advantage plus Q choose 2 times C's ability to win this game is an upper bound on the PRF. And that's our conclusion. So in fact, what we can say, and remember informally before, we thought we were going to have to say that, move this over here, right? This was the informal claim to start with. If E's a good fixed input length PRF, and H is what we thought collision resistant, but it turns out we only need computational AU, then this is true. And in fact, that's exactly what our bound says. If E is a good PRF, it means this is small, and H is computationally AU, meaning this is small, then that's an upper bound on this, so this must be small too, which means this is a good PRF itself. The only thing to note here is that we do have this kind of large scaling, this multiplicative factor in front of this term. Q choose 2 is roughly Q squared. So really this is like Q squared times this. And that tells you that if you want this whole left-hand side to be a small upper bound on that, it means that the hash that you pick better be really good in the sense of being computationally AU, right? This has got to be quite a small number because it's being multiplied by Q squared. Well, we already know, we saw this in class, polyhash, for example, has a bound that's around L over 2 to the n when messages that are asked are at most L blocks long. So if you stick L over 2 to the n in here, this is roughly Q squared times L over 2 to the n And that's not bad. That's still pretty small because that's going to be getting big around square root of 2 to the n time, or roughly, birthday sort of time. So in n is 128, this is still going to be something like, you're still going to need like 2 to the 64 queries before you can start to distinguish this thing from a truly random function. So that's the whole proof. I will conclude by kind of zooming out to give you the whole screen. And I hope that this is helpful to see another full proof done in all the details with lots of discussion.